Welcome to UPSC Maths Optional. In this video, we shall be talking about group homomorphisms. We shall discuss important results, properties, and questions that have come in UPSC Civil Services examination. I will keep it crisp and make sure that this is all that is required for the examination. You need not have to rely on anything else. This will be more than enough for you for this examination. Okay? So let us see what's in this topic. Definition. Let G and G' be two groups. A mapping F from G to G' is a homomorphism if f of A star B equals f of A dot f of B for all A and B belong to G. Here you have to see that this star operation is in the group, which is the domain, and dot operation is in the codomain. Let us see what it is trying to say. So there is a domain and there is a codomain, both of which are groups E and G'. The binary operation in this group is star, and in this group G' it is dot, and there is a function from G to G'. Say that function is f. So what it is saying is f of A star B equals f of A dot f of B. Meaning, if you take any element from here, any two elements A and B, and if you operate A star B, so suppose A star B is some element here, star B, and if you see the image of this under this function, so this will be f of A star B, somewhere here. And what it is saying is this will be equivalent to, if you see the image of A, f of A, and image of B, and if you operate this f of A and f of B, then it will be equivalent to this f of A star. So operate first and then find the image, or you find the image first and then operate. Both will be the same, is what homomorphism is saying. So an observation, f of A equals E dash for all A belonging to G is always a homomorphism. Here E dash is the identity element in the codomain. So this is the trivial homomorphism, where all the elements in the domain is mapped to the single identity element of the codomain. Now let us take a look at some examples. G from R plus to R plus dot. Here R plus is the set of all positive real numbers, defined as G of x equals Ex. Let us see if this is a homomorphism. So what was the condition for homomorphism? G of x plus y should be equal to G of x dot G of y. Y plus because here the group's operation is plus, y dot because here the group's operation is dot. So let us see if this satisfies. What is G of x plus y? E to the power x plus y. What is Gx dot Gy? Ex dot Ey. And we can see that both of these are the same, so that's why this is a group homomorphism. Now let us take a look at another example. Let G be the set of all real convergent sequences. You must have done real convergent sequences in real analysis. Then phi from G plus to R plus is defined as phi of An equals limit of An as n tends to infinity. An is a real convergent sequence. So what do we have to show? Phi of An plus Bn should be equal to phi of An plus phi of Bn. Again, why did we choose plus here and plus here? Because group's operation here is plus, and the group's operation in the codomain is also plus. So let us see if this is true or not. What is phi of An plus Bn? Limit of An plus Bn. And what is phi of An? Limit An. And what is phi of Bn? Limit Bn. Plus. Are these two same? Yes, they are. In real analysis, you must have studied that for finite number of sequences, the sum of the limits equals the limit of the sums. So because of that, both of these values are the same, and because of that, this is a homomorphism. Another example. let S1 be the multiplicative group of complex numbers on the unit circle in the complex plane. So it's a unit circle, so it is cos theta plus I sin theta, or it can also be written as ei theta, right? Tell me in the comments if you understand why it is ei theta. So then this function xi is defined from R plus to S1 dot, where S1 dot is this group, defined as xi x equals eix, and we are asked to show that this is a group homomorphism. Xi x plus y equals eix plus y, which can also be written as eix dot eiy, which is nothing but xi x dot xi y. See, so this is equals this, therefore this is a group homomorphism. Now the properties of group homomorphisms. These are some very important properties. They do not get asked in the exam directly, but they come handy when solving questions. First is identity element is getting mapped to identity element. F of E equals E dash. Then f of A inverse is f of A inverse. Then H subgroup of G implies f of H is subgroup of G dash, meaning subgroup is preserved. If H is a subgroup of G, then f of H becomes subgroup of G dash. The inverse is also true. If K is a subgroup of G dash, then its pre-image is subgroup of the domain group G. Now similar to the third point, N normal subgroup of G implies f of N normal subgroup of f of G. It's not G dash, is f of G. Then N dash normal subgroup of G dash, then the pre-image of N dash becomes normal subgroup of G. G abelian implies f of G is abelian. The converse is only true if f is 1 to 1. G cyclic implies f of G is cyclic. Converse true only if f is 1 to 1. And then order of A is finite implies order of phi of A is finite. Not phi, by the way, it is f, because f is what we chose as the homomorphism. So just make it clear here. If order of A is finite, then the image of A, its order is also finite, and order of the image divides order of the element. Let us try proving the first few. The later ones I would want you to try on your own, and let me know in the comments if you are able to do it. If you are not able to do it, then let me know, we can discuss it. So the first one, we have to show that f of E equals E dash. So for any A belong to G, we can write it as AE equals. Now operating the homomorphism f on both sides, f of AE equals f of A. But since f is a homomorphism, this is same as saying f of A times f of E equals f of A. Right? And now by cancellation law, f of E equals E dash, because E dash is the identity element of the codomain group. So we have shown that FE equals E dash, right? And the second property was f of A inverse equals f of A inverse. Alright, so for any A belong to G, A belong to G, A inverse also belongs to G, right? Because G is a group. And therefore, f of A and f of A inverse belongs to G dash, right? And now, f of A inverse can be written as f of A inverse, right? Because f is a homomorphism. But A inverse is the identity. But from here, the first property, we know that f of E is E dash, right? So f of A inverse is E dash. Now operating f of A inverse on both sides, we get f of A inverse equals f of A inverse. So we have shown the second property too. So you see, it's easy to prove. You just have to use the definition of homomorphism and you will be able to prove these properties. Okay. So just try doing the rest also. Like I said, if you get stuck, let me know in the comments and we will discuss it. Next is kernel of a homomorphism. So let us see what it is. Suppose f is a homomorphism from G to G dash, then kernel is defined as all those elements in G which is mapped to E dash, which is nothing but f inverse of E dash. So let us see what it is trying to say. We have a group, we have two groups, G and G dash, and this is the homomorphism f. So under this homomorphism we know that because this is a group, there will be an identity element E dash, and here there will be an identity element of E. And just now we saw that homomorphism maps identity element to identity element, right? But suppose it's not just this identity element E which is getting mapped to E dash. Suppose there are other elements in G which gets mapped to this. Suppose there is A, B, and similarly there are multiple elements. C is getting mapped to E dash. So there are a bunch of elements that gets mapped to E dash. So you take all those elements which gets mapped to E dash, and the set of all those elements is kernel F. That is, set of all those elements X belonging to G, that is A, B, C belonging to G, such that f of X is E dash. Right? It can also be written as f inverse E dash. Inverse image of E dash under this mapping F. Right? That is kernel. And one thing we can see that kernel is a normal subgroup, because E dash is a normal subgroup because it is an identity element, and we have just seen in the properties that normal subgroup, the pre-image of the normal subgroup is also a normal subgroup. So E dash is a normal subgroup in G dash, therefore the pre-image of it will be a normal subgroup in the group. Right? So kernel will be a normal subgroup of the group. You can also show that the kernel is a normal subgroup by definition. So I want you to try this at home and tell me if you are able to prove that the kernel is a normal subgroup of G by definition. So two things you have to show. First, you have to show that kernel is a subgroup of G, and secondly you have to show that the normality property holds, that is G and G inverse belongs to the kernel, where G belongs to G and N belongs to the kernel. Right? So that is the normality property. If you show those two properties, then you can say that kernel is a normal subgroup of G. Try this and let me know if you are able to do this. Also, before we proceed further, I want to ask you one question. Can you tell me, can the kernel ever be empty? Okay, you have to tell me, can kernel ever be empty? You tell me in the comments if it is possible. Okay, let's go ahead now. Now this is a very important result. What does it say? A homomorphism F is 1 to 1 if and only if kernel contains only one element, that is the identity element. What does it mean? So we saw that kernel is nothing but all those elements that gets mapped to the identity element, right? So what is it saying? That kernel contains only one element, meaning there is only one element that is getting mapped to E dash, and that is the identity element. There is no other element that is getting mapped to E dash. So when that happens, it is 1 to 1, and when it is 1 to 1, kernel will contain only one element. So now let us take a look at the proof. First, the forward implication, let f be 1 to 1 and let x belong to kernel of f. What does it mean? It means that f of x is E dash by definition of kernel, and E dash is nothing but f of E, right? Because f of E is what is getting mapped to E, and because f is 1 to 1, we can write f of x equals f of E to x equals E. So we got that for any element in kernel, it became the identity element, meaning kernel contains only the identity element. Now the other way around, suppose kernel contains only one element which is the identity element. Now we have to show that it is 1 to 1. Now let x and y be elements in the group such that f of x equals f of y. What do we have to show? We have to show that x equals y now. So now f of x equals f of y can be written as f of x f of y inverse e dash, which again, because f is an homomorphism, can be written as f of x y inverse equals e dash. Now what does it mean? It means that xy inverse is in the kernel. So xy inverse is in the kernel. But we already know that kernel contains only one element identity. So xy inverse equals identity, and take this to the other side and we get x equals y. So we got f of x equals f of y equals x equals y. Therefore f is 1 to 1. So we have just shown that when kernel contains only one element, it is equivalent to saying that f is 1 to 1. So that is it. We are done with homomorphisms. Let us see what we studied today. Firstly, we went through the definition of homomorphisms, which was nothing but a function from g to g dash, which was preserving the operations, right? So what was it doing? F of a star b was equal to f of a dot f of b. It was preserving the operations. Then we looked at some examples. Remember, the examples we looked was x was getting mapped to ex, which was a homomorphism. Then we looked at another example where real convergent sequences were getting mapped to its limit, right, which was also homomorphism. Then we looked at some properties. Those properties are very important. You have to remember those properties. Okay, and after that we looked at what kernel is. Kernel is nothing but the pre-image of the identity element of the codomain group, right? Kernel f is nothing but f inverse e dash, pre-image of the identity element of the codomain group. After that we did a very important result which said kernel contains only the identity element if and only if f is 1 to 1, right? So this is what we did today, and that's it. UPSC has not asked any questions specifically from homomorphisms, but UPSC has asked questions from isomorphisms. From isomorphisms, UPSC has asked multiple questions. So in the next video, we'll be doing isomorphisms, where we'll be doing the concepts, examples, some important results, and then we'll be solving previous year's questions as well. So if you have any feedback, you give me. If you want me to do something other than that, write it in the comments and let me know. So that is it. See you in the next video. Happy studying.